Morning, everybody. Welcome back to Abstract Algebra. Plan for today is we're going to continue our discussion of going back into looking at cyclic groups. Now that we've kind of talked about what the order of a group is and what the order of an element is, we're going to use these kind of ideas to prove some more facts about cyclic groups. Due with my usual office hours today, you can't come to that one now, that one's over. 2 o'clock today and tomorrow from 10 to 11 in the morning and 1:30 to 2:30 in the afternoon. Don't forget, you have a homework set, homework 3, that will be due on Friday. And how are mathematicians like the Air Force?
They don't actually do anything.
Get out. No, they both use pi lots.
Wow.
Okay. Okay. Something I forgot to mention on Monday is if you haven't noticed yet, your homework 1 got graded over the weekend. And I kind of switched how I graded it, like part of the way through grading. So some of you got comments where I kind of like, there's like an instructor feedback thing where I just listed a bunch of things corresponding to each time I took issue with something that you wrote. Some of you also got like, and I kind of switched part of the way through to writing a different sort of comment while using the sort of inline grading system where I could like make comments and attach it to individual parts of your page. You should go in and make sure you can see comments in some form. I'm going to be trying to use the inline grading version in the future where I can just like look at your typed version, and if I want to make a comment on a line, I just click a box, click on that spot in the line, and then I can type something. So it should appear when you look at your document, you should be able to see like, oh, Dr. Gerstel made a comment here, click on it and see what I've had to say. Go check and make sure that you can actually see that, because I'm not convinced that you can, and I've had so many problems with Blackboard, me making comments, my students not being able to see it with my other classes this semester. So check that out after class, and if you can't see any comments, I promise I made at least one for everybody. Nobody's perfect. And so go check that out. Let me know if you can't see any comments, and I will try and adjust the options accordingly. I'm going to work on grading homework 2s tomorrow. I probably won't get that done until the weekend, so just so you know. Any questions or comments though before we get started today? Okay, so last time we were looking at this theorem where if G is a group and A is an element of G, where if A has infinite order, remember A having infinite order means that A star A star A star A over and over will never give you the identity element. A has infinite order, then A to the I is equal to A to the J if and only if I is equal to J. And in the second case, if A has order n, meaning A to the n is the identity, but A to any smaller power does not give you the identity. If A has order n, then the group generated by A is going to consist precisely of the elements, the identity A squared up to A to the n minus 1. And we also said that A to the I is equal to A to the J if and only if n divides I minus J. Meaning if you have 2 powers of A that are equal to each other, then the difference in those powers, I minus J, has to be a multiple of n. And last time, I do believe, we had gotten to this point. We had proven all of part 1. We had proven the first half of part 2. We showed that the group generated by A is this set. But we still needed to prove the last statement, that A to the I equals A to the J if and only if n divides I minus J. Hello. So, let's start with that. So we're kind of in the second half of part 2. Part 2.5. So first part I want to prove is I'm going to do the hard one first. We're going to suppose that A to the I is equal to A to the J. And our goal is going to be to show that with this assumption, if we have two powers of A that are equal to each other, that I minus j has to be a multiple of n, has to be a multiple of the order of the element A. If a to the I is equal to a to the j, what has to be true about a to the I minus j? If we were to say multiply both sides of that equation on the right by a inverse j times. A to the I equals a to the j, and we cancel out j copies of a on both sides.
Is it going to be identity?
Is indeed. Then a to the I minus j has to be the identity, or a cursive L, apparently, by cancellation. Because you can just cancel out j copies of a to the j on both sides. Or yes, Nick, if j is negative, you can multiply by a to the negative j. You can multiply by a inverse negative j times from both sides. So a to the I minus j is the identity. And what does that tell us? Well, here we're going to use our friend that we used last time, the friendly neighborhood division algorithm theorem, which says since I minus j and n are both going to be integers, the division algorithm tells us, well, if I minus j is an integer and n is an integer, then we can find a q and an r such that blah, 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 the division algorithm theorem. The quotient and remainder terms that the division algorithm theorem gives us. There must exist integers, q and r, with I minus j equal to qn plus r. So here we're basically saying we can, if I minus j and n are both integers, we can divide I minus j by n and get a unique quotient and remainder term. So I minus j is equal to qn plus r, and we know that r has to be greater than or equal to 0 and less than n by the division algorithm. So again, this just comes from the fact that I minus j and n are both integers, and the division algorithm theorem says we can, given any two integers, we can always find a q and an r that'll make this equation work with r satisfying this inequality. And the fact that r satisfies this inequality is going to be very important to us. The division algorithm theorem also tells us that this q and r have to be unique with this property, but we're not going to need the uniqueness part of that theorem. We just need that there's at least one q and r that'll do this. So I minus j is equal to qn plus r. So then a to the I minus j, which by the way, we said was the identity, has to be equal to a to the nq plus r, or qn plus r, order doesn't really matter, which we could split this up and get a to the nq times a to the r. What is a to the nq going to do? Well, it's going to be a to the n, taken star itself q times. Keep in mind this is a to the n star, a to the n star, a to the n star, a to the n q copies of it. And we'll have an a to the r. And what do we know about a to the n? I'm going to look at the statement of the theorem. What are we going to assume? What did we assume about a that's going to tell us exactly what a to the n has to be? Okay?
The identity.
Has to be the identity. Why does it have to be the identity?
Because a to the n minus 1 is the last. I don't know how to explain that.
Go up a line. statement of the theorem.
Because the order of A.
Yeah. We assumed that A has order n, which is a finite number n. By definition, that means A to the n had to be the identity. So this just comes from the fact that the order of A is n. A to the n has to be the identity. Identity to the q power, you could take identity star identity over and over again. That's just still going to be the identity. And so what we end up with is that A to the r has to be the identity. Everyone okay with that so far? Just kind of split up A to the I minus j. We know A to the I minus j is the identity from what we said over here. And the rest of this is just kind of coming from using the division algorithm theorem and using the fact that A has order n to split this up in this way. We made an argument somewhat similar to this in class on Monday when we were proving the first half of number 2. So A to the r is the identity. So A to the r is the identity. The order of A is n. And since, what else is the other thing? And since 0 is less than or equal to r is less than n, I think we can say something very specific about r. Because notice, the fact that A has order n means that, this is kind of as an aside, k equals n is the smallest power greater than 0, such that a to the k is the identity. So we know we're taking a to some power r and getting the identity. We know that r is strictly less than n, and we know that n is the smallest positive power, such that a to that power is the identity. It's not going to tell us about r. If a to the n is the smallest, if n is the smallest positive power, to which a to that power is the identity, but we just found some r smaller than n, and a to the r is the identity. What has to be true about r in order to make all of this work? Right?
It's 0.
R has to be 0. Because if r was anything greater than 0, we would have a smaller positive power than n, to which a to that power is the identity. And that can't happen. The fact that n is the smallest power, the smallest strictly positive power, to which a to that power is the identity, combined with the fact that, well, we have something strictly smaller than n, where a to that power is the identity, the only way all of this can occur is if r is exactly 0. Any questions or comments about that? A little bit tricky. We're kind of using 3 separate things here to make this argument. Well, if r is equal to 0, then we're basically done with the first half of our proof of this last sentence, because then we can say I minus j is equal to qn plus 0 is equal to q times n, hence n divides I minus j. Because, well, we just showed I minus j has to be a multiple of n. Since in the qn plus r formula, we showed r has to be 0, meaning I minus j is just q, whatever our quotient is, if that's an integer, times n. So we've shown that if a to the I is equal to a to the j, that tells us n has to divide I minus j. What else do we need to show if we want to finish our proof of this big old theorem? We've shown if a to the I equals a to the j, then n divides I minus j. We still have one more thing we need to prove.
Do the second half, then prove first.
Bingo. We need to also show that if n divides I minus j, it has to be the case that a to the I equals a to the j. But fortunately, that part's a little bit quicker. Because we can just say, if we suppose that that n divided I minus j, well, then we can say I minus j is equal to qn for some integer q. That's by definition of n divides I minus j, that I minus j is some integer multiple of n. Hence, a to the I minus j is going to be a to the qn, which is again a to the n to the q, which is the identity element to the q, which is the identity. So we get a to the I minus j is the identity element, and then we can multiply both sides of that equation by a to the j and get a to the I equals a to the j. Put a big old filled-in square. That's one kind of mathematical lingo for the proof is done. We have finished proving the theorem. Neato, mosquito, we can all go home now. You can't go home. We still have a lot of class left. It's like a QED at the end of your proof. Lots kind of different ways to write that. I'm a fan of the whole filled-in box at the end of my proofs. Make it clear what proof. So we proved our if and only if statement by showing if a to the I equals a to the j, then n divides I minus j. We also showed that if n divides I minus j, then it has to be the case that a to the I equals a to the j. And that's necessary to prove an if and only if statement is that you prove from left to right and from right to left. Questions or comments about any of this? It's a big proof. I mean, I just proved the last sentence and it took me like a good 15 minutes to do. And we had kind of a lot of one in the first half of two was last class. Everybody doing okay? Or so overwhelmed that they don't have any good questions, feel like they have any good questions to ask right now? Okay. Happy to talk to you about any of this in office hours. I realize this is a very technical argument, getting very deep into multiples and things dividing other things and using the division algorithm. So if you don't understand this right away, you might want to come back to it later and take a second read through. But this theorem is going to be useful. Because now it is time for a couple of corollaries. Corollary. In any group G, if A is an element of G, the order of A is equal to the order of the group generated by A. So this is something that we this is a word we haven't really seen before, corollary. In this class at least. Anybody who's seen this word before, can you share what the word corollary means in this context? Yeah, Peter?
It's something that you didn't set out to prove, but you proved like inherently what you proved. Is that correct?
Technically, what you just described, I would call a schooling, which is a much fancier name that nobody ever uses, and I don't know how I know that word. I would say corollary, I would say your answer is close to right. It's something that follows very quickly from a previous theorem. The part I disagree with is it's not necessarily something we didn't set out to prove. In fact, in class on Monday, this is something I said, I want to prove this, and I'm going to prove it by way of proving a much bigger, scarier theorem. But here, the word corollary just means it's a result that follows pretty easily from a much harder result. So in this case, our theorem was a big, scary thing to prove. Our corollary kind of follows immediately because, well, If A has order n, clearly the group generated by A is something with n elements. It has an e and a to the first and a squared up to an a to the n minus 1. 1, 2, 3, n. I count n things in there. And if A has infinite order, it's a quick argument to show that the group generated by A from this has to also have infinitely many elements in it. In fact, I'm not even going to prove this one. I'm just going to do one more example so everybody remembers what this is saying. Oh, let's see. What's a good one? You have a question about this group on your homework. Let's do an example of it. N, the group of rational numbers, non-zero rational numbers, which is a group under multiplication. How many? So the identity here is going to be 1. How many times, if I were to take 1/2 times 1/2 times 1/2 over and over again, how many times would I need to multiply a half by itself in order to get to 1?
0 times.
0 times? Gadzooks. What does that even mean? You're right. 1/2 to the 0th power in this group would be 1, using our notation. Is there any positive number of times we could take a half times a half times a half over and over and somehow end up at 1? I don't think so. That's going to be infinite. Since 1/2 to the k is not equal to the identity for any positive value k. So that's what it meant for something to have infinite order. And similarly, if we were to take the group generated by a half, that would be the number of elements in the set. A half, a fourth, 1/8, 1/16, going on forever, as well as 2, 4, 8, 16, going on forever, and 1. How many elements are in this set? What's that?
Like an infinite amount?
An infinite amount. This list would never end. If I kept multiplying by half over and over, I'm going to always keep getting new numbers. So here's a case where the order of a half is infinite, because 1/2 to any power is never going to give you the identity. And similarly, the group generated by a half has infinite order, and the group having infinite order just means there's infinitely many elements in this group. So here's a case of those two things matching up. In the case of the infinite order. Let's see, what's something with finite order? How about -1? What would the order of -1 be in this group? In other words, if I were to take -1 multiplied by itself over and over, how many copies of -1 would I need in order to get to the identity of 1? Peace out, Peter.
I was saying 2.
Oh, your answer is you're claiming that there are 2, that it's only 2?
If I'm right, then yes. If not, I'm telling you peace.
Okay.
Had you my head.
You are correct.
Okay.
And also peace.
Right.
I agree with your answer and with the sentiment. Yeah, so this case is going to be 2. Don't be fooled. This is order, not absolute value. Since k equals 2 is the smallest positive power, is the smallest, let's say, k, positive integer k, such that -1 to the k is equal to the identity element here, 1. -1 to the first, not the identity. -1 squared, that's 1, that's the identity. So -1 has order 2. And if we were to look at the group generated by -1, well, let's see. We're going to get -1 -1 squared, which is +1. We would also get the inverse of -1. What would the inverse of -1 be in this group? Oh, hey, it's its own inverse. So we don't need to worry about adding powers of -1's inverse because we already did that. But wait, we also need to add the identity element. Oh, wait, we already have the identity element. Group generated by -1 only has 2 elements, and so its order is going to be 2. So that's what this we just proved with this corollary as part of this big theorem, is that an element of infinite order is going to generate an infinite subgroup of the overall group, and an element of finite order, n, is going to generate a group of order n in the same way. Questions or comments? Okay. Another quick corollary, and this one we'll actually write a short proof for. So, where this one is going to be another result that follows very quickly from the previous theorem, is going to be that for any group G, if A is an element of G with order n, then whenever A to the k is the identity element for some integer k, n must divide k. In other words, if A has order n and some power of, and the only way to take A to some power and get the identity element is if that power was a multiple of n. Technically, this is an if and only if. But we're mainly interested in this part because the backwards direction is pretty easy. All right, here's our proof. Since A to the k is, actually let's start by saying suppose A to the k is the identity. Then since A to the k is equal to the identity, which is also going to be equal to A to the 0 by definition, A to the k has to be equal to A to the 0. So what does the thing we just proved at the end of number 2 tell us? If A to the k is equal to A to the 0, then n has to divide what?
K minus 0.
N has to divide k minus 0, which is the same as saying n divides k. By the theorem, we know n divides k minus 0, the difference of these two, i.e. n divides k. Since k minus 0 is k. Boom. 1, 2, 3, 4 line proof. That would have been much harder to prove had we not had this theorem to help us out along the way and do the bulk of the work for us. Okay.
Is there perchance a schmancy symbol that means divides? Nice, thanks.
Is that fancy enough for you?
Works for me.
I'm trying not to use too many symbols. Like I could also be throwing in like paroles and there exist and such that's, but I'm trying not to overwhelm you too much with just throwing different symbols into all the proofs. But n divides k, shorthand of that is just n vertical bar k. I should just start using that. That one's not so bad. And as a quick example, let's say in D4, we know that the order of R is equal to 4, because 4 is the smallest number of times you can compose R with itself and get the identity, where R here is a 90-degree rotation of a square. Thus, this, according to this corollary, we know that if R to the K is the identity element, we know what has to be true about K. Since R has order 4, if R to the K is the identity, what can we say about that K, that power of R for which we're getting the identity, according to the corollary?
It's a multiple of 4.
It's multiple of 4. This pleases you, Gabe. 4 divides K. So K can be 4, 8, 16, 20, 24, etc. It can be 4 billion, but it can't be 4 billion and 1 because that's not a multiple of 4. Questions about this corollary? All right. Hope you all enjoyed this big theorem, because now it's time for another big theorem. So the next big theorem is going to be involving some facts about the relationship between a to the k and the GCD of k in the order of a. That sounded like a cool rhyme. I should make a rap that's which I said that sentence. So here's the theorem. We're going to let G be a group. A is going to be an element of G, and we're going to suppose this time that A has finite order n. And the claim is going to be that for any integer k, first, that the group generated by a to the k is going to be the same as the group generated by a to the GCD of n and k. And second, that the order of a to the k is just going to be n divided by the GCD of n and k. So it may feel like a simple little theorem, just a way to relate. If A is order n, then a way to relate the order of A to some power k is just going to be something that we can determine as a relationship between n and the GCD of n and k. But this theorem is going to be the big one that lets us prove the fundamental theorem of cyclic groups. Let's get cracking. So I'm going to prove part 1. So I'm going to say, let's see, let G be a group, A and G, order of A is equal to n, some finite number, and k an integer. Just our introduction, we're setting up all the pieces. So because this proof is going to involve writing down GCD of n and k like 100 times, I'm just going to use a variable d and to say let d be the GCD of n and k. The only reason I'm introducing a new variable is because it's a lot easier to write d 100 times than it is to write GCD of n and k 100 times. And we're also going to let r be k over d. So this is complicated already, and we haven't even done anything yet. It's because I'm introducing a bunch of different variables. But I'll try and go through carefully and explain each variable's usage as we need it. So our goal, at least in number 1, is we're going to show that the group generated by a to the k is equal to the group generated by a to the d, where d is the GCD of n and k. It's going to be our goal. To do that, we need to show everything in this first group is an element of the second group, and that everything in the second group is an element of the first group. Basically, we're going to show each group is a subset of each other, and that'll tell us then that they have to be the exact same group. the exact same subgroup of G. All right, easy one first. If R is equal to K over D, then that tells us that A to the K power has to be equal to A to the dr power, which, lo and behold, is just A to the d power to the r, which is going to be an element of the group generated by A to the d. So in other words, I just took A to the k and showed that it had to be that A to the k at a minimum has to be in the group generated by A to the d. Well, because A to the k is just, well, that's just a power of A to the d. And any power of A to the d has to be in the group generated by A to the d, by definition. Well, then we can say that since A to the k is an element of group generated by A to the d, I claim by closure anything in the group generated by A to the k has to also be an element of the group generated by A to the d. So in other words, if A to the k is an element in this group, then any power of A to the k is also going to be an element in this group by closure of this thing as a group. Basically saying every power of A to the k, if A to the k is in a group, any power of A to the k also has to be in that group because of closure and inverses being things. Therefore, that subgroup, or that group is a subgroup, or is a subset of that group. It is a subgroup too, but we only need subset for our argument. So everything in the A to the k group has to be in the A to the d group. Any questions so far? That was the easy one. Now for the fun one. We're also then going to show that everything in the A to the d group is also contained in the A to the k group. And to do that, we really just need to show A to the d itself has to be an element in the group generated by A to the k. So, since D is equal to the GCD of n and k, we know automatically there exist some integers, s and t, such that D is equal to ns plus kt. Y'all remember seeing that theorem? The one that said if you have GCD of n and k has to be able to be written as a linear combination of n and k? Y'all remember that theorem, right? I'm trying to see how many of you I can get to nod because you're all liars. We never talked about that theorem.
Man.
You may have seen it before in another class, but not in this one. This is going to be from a theorem we never discussed, which I don't feel like, which if we wanted to prove would take us like 40 minutes, and this would be literally the only time we would use it. So I don't feel like taking like most of a class just to prove this theorem. We're going to use one time, and it's not really going to be too relevant otherwise. So basically, D is, we know we can write as a linear combination of n and k, meaning there exists some s and t such that D is equal to ns plus kt. Alright, D is equal to ns plus kt. Then A to the D, by definition, is going to be A to the power of ns plus kt, which is equal to A to the ns times A to the kt, which is equal to A to the n to the s times A to the k to the t power, Maybe I'll pause for a second so you all can catch up. What do we know about a to the n? It's going to be the identity. Why? Because a has order n. So since a has order n, a to the n is the identity. So this just becomes a to the k to the t power. The s ends up not mattering because e to any power is just going to be e. And so what we've shown is that a to the d power has to be some element of the form a to the k power to some power t, which is going to automatically then be an element in the group generated by a to the k. Because the group generated by a to the k has to automatically contain any element of the form a to the k to any integer power. Questions or comments so far? Thus, a to the d is contained in the group generated by a to the k. Hence, by closure, the group generated by a to the d has to be a subset of the group generated by a to the k. Basically saying, since a to the d is an element of the group generated by a to the k, any power of a to the d is also going to be contained in the group generated by a to the k, and thus everything in this set is also contained in this set. And so, finish off part one here, we could say that since everything in the group generated by a to the k is contained in the group from generated by a to the d, and everything in the group generated by a to the d is contained in the group generated by a to the k, thus these two groups are equal. And as a reminder, d was just the GCD of n and k. Boom, number one. Are you all ready for the first exam when I asked you to write a proof this long on the exam? Yeah, this is a long and complicated one. For proofs like this, these are not ones I'd expect you to be able to come up with on your own, because they're very long and complicated. I hope, though, that you can kind of get something out of looking at the proof and hopefully being able to understand the different steps of the proof and kind of how they relate to previous things we've talked about with the exception of this thing. That's kind of what I'm going for. So is that you kind of are able to sort of follow along with the proof, even if you've never in a million years be able to come up with something like this on your own. I think this is a good time to stop and tell you about the person who who basically came up with most of group theory. Évariste Galois, French mathematician, died at the age of 21. So if he can do it, you all can. Yeah. You know how he died? He died in a duel, like Hamilton.
What?
What, Prime Minister?
The Prime Minister. Fun fact, he was killed by Aaron Burr, just like Hamilton. No. Another kind of person he went to school with who didn't like him.
I understand that feeling.
You and Abby are not allowed to do it.
You're the one who calls me rivals.
Yeah, well, not that kind of rivals. Not rivals who play pranks on each other, not like the
Rivals who duel.
Anyways, this is getting far away. So that is a fun fact. A lot of what we're doing in group theory was come up with, at least like the bare bones of which was come up with by this guy who died at the age of 21 in the duel. Kind of nice. We're going to talk about him like more later in the session.
Wait, so how old was he when he was coming up with this stuff?
I think he was about 12 or 13.
No.
No, he was like, no, this is like in like the couple of years before his death.
Why?
Say what?
Seems like I feel so inadequate now.
Good, that was the point. If it makes you feel bad, I'm like 10 years older than Galwal was when he died, and I haven't done like a hundredth of what he contributed to math. So that's how I feel.
Yes.
You got this. Yeah, maybe start. Maybe start.
Part 2. We've shown that a to the k and a to the GCD of n and k are going to have to generate the same group. We now need to show that a to the k has order equal to n divided by the GCD of n and k. So now, for our next trick, we're going to note that if we were to take a to the d and take it to the power of n over d, well, that's just going to give us a to the n power, which is that n d. So if a to the, we can say something about the power of a to the d, namely that a to the d has order less than or equal to n divided by d. We don't necessarily know yet that a to the d has order equal to n over d from the fact that a to the d to the power of n over d is the identity. How many times did I say the syllable d in that sentence? We know a to the d has to have order less than or equal to n over d because n over d could be a multiple of the order of a to the d. We don't know that n over d, in other words, is the smallest power such that a to the d to that power is the identity. We just know it is a power that does that. So whatever the order of a to the d is, it has to be less than or equal to that. Also, I claim that if I is some number between 0 and n over d, then di is less than n, it's Princess Di. Hence, a to the d raised to the I power is going to be equal to a to the di power, which is not the identity. So here we're basically saying a to the d power can't have order less than n over d, because a to the d to any power smaller than n over d can't possibly be the identity. Why is that? We're running low on time, so I'm going to answer my own question. Because di is less than n, and n is the smallest positive power to which a to the d to that power is the identity, or which to which a to that power is the identity, that tells us this can't possibly be the identity, since the power we're taking a to get the identity has to be something that's either 0 or that's greater than or equal to n. So if di is strictly between 0 and n, this is not going to be the identity. Thus, that tells us that the order of a to the d has to be greater than or equal to n over d. And hence, a to the d has to have order equal to n over d exactly. Dr. Gerstel, part 2 says we need to find the order of a to the k, not the order of a to the d. Check this out. I claim that the order, or that the group generated, that the order of a to the k is going to be equal to the order of the group generated by a to the k. That comes from our first corollary for today. A to the k, the element, and the group generated by a to the k have to have the same order. But that's going to be the same as the order of the group generated by a to the d. Why? Number 1 here. A to the K and A to the D generate the same group. That was what we just proved over here with number 1. And the group generated by A to the D is going to have order equal to the order of A to the D, again by corollary 1, which we just showed is equal to N over D, which is in fact N over the GCD of N equals O. A to the K has to have order equal to the order of A to the D, because they have to have the same order as the groups they generate, and they generated the same group. I think that's cool. I like this argument. And so A to the K is the same order as A to the D, which is this N over GCD of N and K. Dr. Gerstel, why do we care about this? This seems stupid and pointless. This is going to be a big part. This is going to save us a lot of work in proving the fundamental theorem of cyclic groups, knowing about the order of A to the K versus versus the order of A and the GCDs and OMGs and blah, blah, blahs, and get out of here. I'll see you on Friday. Friday, we're actually going to start proving the fundamental theorem of cyclic groups.
Seriously.